When evaluating a function from a graph, it's helpful to remember this f of x equals y in our function language. Remember that x is our default input variable, y is our default output variable. So in a case like this, I'm going to see that -1 is in the position of x, and therefore what I'm looking for is a y value corresponding to x equals -1. I find -1 on the x-axis and trace vertically to the graph. When I trace vertically, my x is not changing. Then I try to estimate that y value. In this case, it's something I have to get a ballpark figure for. We'll say about 1.3. For the next one, I again have x equals -3. I trace vertically to the graph, which in this case is down. Doesn't matter whether it's up or down, as long as we're not changing the x value. Then we trace horizontally to read the y coordinate. In this case, we don't have to estimate. It looks like it is exactly -4. For the domain and range, again, I want to remember that the domain is the set of all x values. So I'm looking for the leftmost x value on the graph. And I can see that I have an endpoint here at -3, so that's where my graph starts. I'm going to draw this on the x-axis. I will keep going until I get to either a right endpoint of the graph or an arrow indicating that the graph keeps going. In this case, I have a right endpoint at 5. That's where my graph stops. It looks like the domain is everything between -3 and 5. I can see that those endpoints are included. Therefore, in interval notation, I'm going to use closed brackets to express this set. So this is the interval from -3 to +5. And if I wanted to write this using set builder notation, I could also do that. We want to at least be able to understand the relationship between interval and set builder notation so that we can recognize a set in set builder notation. This is the set of all x such that -3 is less than or equal to x, which is less than 5. Sorry, less than or equal to 5. And I'll darken my interval notation here with this nice black color also. Make it real pretty two-toned green and black. Okay, so for the range, I'm going to do a very similar thing, but on the y-axis. The only thing with the range is that it may not stop at an endpoint of the function. We can look at this and see that this endpoint, the left endpoint, is also the lowest point on the graph. So I'm going to start coloring in my range from there, but I don't stop when I get to where that right endpoint is. Instead, I can see that it really goes up to where that kind of hilltop is, right? So I can identify this range as starting at -4 and going up to +4. And therefore, I'm going to write my range using interval notation as the interval from -4 to +4. With, again, square brackets. Both of those endpoints are included. Even the point at the top of the hill is a point on the graph, and therefore we would use a square bracket there. And if I wanted to write that using set builder notation, that would look like this. The set of all y such that -4 is less than or equal to y, which is less than or equal to 4. I should use the y variable for this set because we're talking about range. Make sure that your interval endpoints are in the correct order. We don't want to say from 4 to -4. That's not a valid interval. And it can cause some big problems if we mess up our endpoint order, right? All right, so make sure we get those endpoints in increasing order. With the x-axis, it usually happens very naturally because we're going from left to right. But with the y-axis, we have to think from bottom to top, which might be a little bit less natural. All right, looking at this next one, a little bit more involved. We're just doing domain and range this time. A little bit more involved because we do have that arrow. So for the domain, I'm looking for the leftmost point, which I can see is here at -4. And I'm going to keep going, going, going until I get to another endpoint or an arrow. And I can see in this case I get to an arrow. Because there is an arrow on the graph, I'm going to put an arrow on my domain also. And it looks like this is my interval from -4 to infinity. For the range, I'm going to do the same thing. Look for a highest or lowest point if there is one. It looks like there's a highest point, so I'm going to start here and go down. And I can see that in the down direction, that arrow also seems like it's pointing sort of down. So I'm going to accept that as the trend in the graph. And it looks like I have everything below 3, but again I need to, for my interval notation, make sure I write these in increasing order. So that arrow is approaching -infinity, and that right endpoint is 3. This range is the interval from -infinity to +3. So now that we know how to evaluate functions that are defined by graphs, we're ready to also address the question of whether a relation that's defined by a graph is a function. So, looking at these two graphs here, we can start to think about what would be happening if I were given an input x and trying to evaluate the function there. I can see that I would come up to this point xy. X would be my input, Y would be my output, right? If I compare that to what happens on the second graph, let's say that I have some X value that is somewhere inside this ellipse, and I'm tracing to the graph to get my XY, and I recognize that, oh, there's not just this one, so I'll call this Y1. I also could have gone down and gotten a point on the graph. So I'm going to call this x, y2. It's the same x in both cases, so this is what we have, the input x mapped to two outputs, y1 and y2. So we can tell by looking at this and by thinking about the definition of a function that this second one appears to violate that definition. This is not a function. In this first one, it doesn't matter where we draw that x. When I trace vertically to the graph, I'm still just going to get 1 point, and therefore 1 output. So this one is a function. We'll write that right here. So because the process of evaluating a function for an input x is the same as drawing a vertical line, we have this test that we call the vertical line test. If it's possible to draw a vertical line that intersects the graph in more than 1 point, then we would say that it is not a function, that graph, that relation is not a function. If it is not possible to draw such a line, so let's use a different color here. If every such line we draw that's vertical only intersects the graph at 1 point, then we would say that it is a function. So we can see with these vertical lines here how we would apply the vertical line test.